let's see here. Last minute. So let me reduce the voice and let's start. So I'm going to be looking at Apache Flink. So I'm starting with the Apache Flink. I want to learn basics of streaming and how Apache Flink comes into the picture. We'll go from basic, very basic, to looking at all the features it has first of all, and then maybe later look at Apache Flink's internals. We'll look at how the storage works, how the internal structure of the code is, what are the different components. I have my iPad, where I can show you the different architecture and we'll focus on different design decisions that's been taken. We look at different Jira for the Apache Flink, different design documents, what's going on recently. We'll also try to look at a couple of GitHub issues, maybe just to look at what's going on there, recent issues which are not solved. So that's the plan for right now. So let's get started. Let's see how much I can continue with this, but let's start. Okay, so this is the link for Apache developer trainings. I have shared this link into the description of the video, so you can probably see the description here. Right, so okay, so let's start with this. We'll go over one by one. What's this? Okay, so intro 50 million, blah blah blah. Okay, so let's go over this. Okay, let me switch off my dark regions so that it's okay. So let's go back. Come on, man. Let's make it first thing better. Okay, anyways. So let's start with the basic stuff. Okay. We're off. Okay, I'm just registering my screen. Okay. Okay. So let me go with this. Okay. Okay, let's fix this. Okay. Come on, man. Okay, so let's move this to my other screen and let's just start with the basic stuff. Let me open my chat window also here. So chat. Okay, is it upside down? Okay. Come on, man. Okay. I cannot even close it, man. Okay, docs, reset UI. Okay, so let's see. It is able to show stats. Okay. Okay, and let's chart. What happened? Oh, come on. Okay, let's do that. Okay. Docs, chats, docs, chat. Okay, now it is coming. Convenient. Okay. Okay, let's see how this looks. Anyways, no BS problem, so that one thing about it right now. Let's get started with the Flink stuff. So, okay. 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 That's fine. Look at the chart and okay. Okay. So we use this stuff first. Okay. Okay. Okay, I think. Huh. Okay. So that's one. Difficult. Okay. So let's put it here as well. Okay. Now, okay, let's start. Let me start this thing also. Okay. So Flink is an open source stream processor. Okay, effective. Okay. Okay. 1 plus trillion event process pattern. Contributors. Okay, fine. Okay, verifying its runtime parallel. It's an overview. Okay, so let's look at stream replacer, stateful stream processing, stream analytics, data, event-driven applications. Okay, so data is coming from here, going into Flink runtime, stateful computation over data streams, and then it is output, analytics, processing, stream analytics. Okay, fine. Then overview of Flink, its runtime is based on a parallel data flow engine supporting stateful computation over data stream. Flink is not a stream storage provider. Instead, Flink supports a diverse set of connectors for both input and output, and it supports a wide variety of use cases. Connectors include event queues, file systems, databases, in addition to a general purpose low-level data stream API. Specialized APIs have been developed to support two common families of use cases: stream analytics, okay, which are supported by Flink's relational API, okay, the SQL and table APIs, okay, and streaming analytics, what's called streaming analytics, okay. Okay, event-driven applications which are supported by stateful functions APIs. What is that? Okay, first of all, let's look at streaming analytics. The processing and analyzing of data records continuously rather than in batches. Generally, streaming analytics is useful for the types of data so that sends data in. Okay, so let's look at this thing. Stream analytics works. Okay, stream analytics, also known as event streaming processing. Event streaming processing is the analysis, also known as event streaming processing. Event stream processing is the analysis of huge pools of current and in-motion data through the use of continuous query. Called event streams. These streams are triggered by special events that happens as a direct result of an action or a set of action like financial transactions, equipment failure, or social post, or a website click, or some other measurable activity. The data can originate from the IoT transaction cloud application, web directions, mobile devices, and machine sensors. By using stream analytics, platform organization can extract business value from the data in motion just like traditional analytics tools would allow them to do with the data at rest. Real-time streaming analytics help a range of industries by spotting opportunities and risks. Okay, so event is produced here, event queued here, stream ingestion is happening here, stream analytics is done here, then the storage and presentation action. Okay, data visualization, keeping an eye on the most important company information can help organization manage their key performance KPIs on a daily basis. Streaming data can be monitored in real time, allowing companies to know what is occurring at a very single moment. Okay. In case of an increased competitiveness, cutting preventive losses, analyzing routine business operation. How can many customers do you have in your store at this point, and which vehicle in our fleets are using the most fuels, and okay, that's fine. Finding missed opportunities can help companies to the hidden patterns cross-sell connect based on what the information presents, creating new opportunities, bring the type of first. Okay, got it. That's fine. That's basic, I guess. Yeah. Okay. Okay. So just supported by the Flink's relational APIs. Okay. Which are supported by the stateful function APIs. So there's streaming APIs, which is stream analytics APIs, and there are stateful function APIs. Okay, which is event driven. Stateful and event driven. Okay. So now let's look at Flink's data stream APIs. So what we are doing here is we are telling that, you know what, get this particular, we are adding the source of the stream. So we are adding this Flink Kafka consumer, which consumes the events, and this events gets mapped for each line, each message passed and provided as events. Events, and then these events are transformed. Okay, so event is transformed. So key by. There must be a window in which we are looking for and process in that window my window aggregation function. So in that window we'll provide all the events to a particular function, which will process all the events in this function. And we are creating like key value pairs out of these events, I guess. So for example, we got a message, we pass that message, we create an object out of that message, which is event, right? So, and in that event we have this ID and we have certain other object values, internal values, right? So what we do is we create a key value pair for each event, and key is the ID of the event, and then we say that, you know what, look at this particular window size, which is in this case it's 10 seconds. So all the events in that 10 second is sent to my window aggregation function, and after that we get the statistics from those events for each like 10 seconds or 15, whatever time frame that we are looking at. And what we'll do is we will add a sink for that particular. So we added source from the Kafka, right? We are going to add a sink as well, whether it's Kafka or database or file system, anything like that. So let's look at what's happening here. So there is a source, which is source operator, which is a stream. This is data stream, and it's getting passed to map. Each stream message is transformed by this, and processed and sent to the sink. Okay, so let's look at this. With the rather low-level data stream API, you are dealing directly events at a time, streaming, managing state, and working with time and timestamp. As you use the data stream API, the code you write describes direct acyclic data flow graph called job graph. As you see, tool you run is considered direct acyclic data flow graph called job graph. When the main method of your application is run, it constructs a job graph which then executed by a Flink cluster. This diagram illustrates the one-to-one correspondence of different sections of the code to the stages of the job graph described by that code. So I guess this is the job graph, the direct acyclic graph. And let's go forward. Okay, so let's look at how this particular SQL query is converted into API queries. So it's doing select by user count by URL. So let user count URL as count from clicks group by user. So for each user, it's trying to count all the URLs. So from here, for the similarity, what we can do is from this particular table, we can group it by user and then select this particular URL.count. So, so this means it will give us the count of the URL. Interesting. So it's passing that string as well. So unified APIs for batch and streaming data. So this particular code can work for both batch and streaming data. Okay, the same thing, of course, like SQL query, something like table API. So it can be implemented for a streaming. We need to provide a source and we need to provide a sync. That's it. Source could be a data source as well, for example, static data database, or source could be a messaging stream, which was in the last case, which is a Kafka store. Okay. Um, okay, let's query yields exactly the same whether it's input is static or okay, fine, that's fine. We are operating at a high level of stream, but both examples are also compiled into a. So ultimately what happens is this is also passed and after passing created a job graph which is directed acyclic graph. So the same case happens with the table APIs as well. So okay, Flink stateful function API, aka state function, stateful functions functions API, an API that simplifies the building of distributed stateful application. Okay, so we have this streaming data, right? Let's say after streaming certain messages, we want to store certain state as well. For example, we want to store whether the last 10 second, what was the, let's say for example, payment system, right? So for example, a particular user transacted $500 in last 10 seconds, and then in next 10 seconds, the same user transacted, let's say $1,000. Let's say this is the pattern that we are looking at. Then we can identify by maintaining state that this is the user which, and this is the last transaction this particular user had, and in the current state, this is a user, and this is the same user, and it's trying to transact $1,000. Then we can identify these kind of states, and we can actually create an event or create an output, I guess. Native front end design for Solid, that's fine. Building block, remote functions, small piece of logic that represent entities. Okay. Multi-language instead of Bitcoin can be implemented in any language. Okay, that's fine. Dynamic messaging, arbitrary communication between functions. Arbitrary communication between functions. Dynamic messaging. Hmm. Okay. What's called dynamic messaging? So, couple of functions can talk to each other internally, I guess. Okay, let's see what it's consistent state. No database required. So it stores a particular state which is consistent and it doesn't require database to store it. So function have persistent local state, globally consistent with exactly one guarantee. Hmm. Okay, so it has internal storage which is not based on any database but stored locally. Let's say it is replicated across multiple nodes, then that's the state is also consistent. For example, if this particular node happens to be faulted or something like that, then the other node can take its place and simply say that I have also the consistent state. You can use that. Okay. Okay, multi-language support. That one. So what's the remote function that we are looking at? So I'm not sure. Yeah, okay. Wow. Hmm. Okay. We'll use case ETL analytics, streaming an ETL to data warehouse. So we are streaming certain logs, and we need to put it into a data warehouse. Usage, metering, and billing. Okay, master. So first use case is streaming ETL logs to data warehouse. We just need to put those logs to data warehouse. And another thing is usage, metering, and billing. So let's say you're getting logs and you're seeing that this is a user which has, let's say, stored this amount of data or use this amount of network data. Let's say we are talking about cloud. As in the cloud, billing happens. Sometimes billing happens with the data transfer, then the size of the storage is used. You can create those events when the user uses it and send it to our Flink cluster, and in that cluster it will um, log those data, create a bill out of it. So for example, each 10 seconds, 15 seconds, 20 seconds, whatever time stamp we are looking at, it will say that this is the total amount of data which was processed by this particular user, and um, and we will charge this particular bill for that particular usage. Okay, so master data management. How does data management is used? So here some example. It wasn't that long ago that it was feasible to do this thing in near real time. Okay, it's easy to see how companies like Lyft and depends on being able to react instantly to data. What's interesting, however, is how many companies in more traditional industries such as banking and retail are finding real business values and transforming their businesses to be more responsive. Okay. Okay, so this analytics side of it, this is event-driven side of it. So there is this fleet management and logistics. So how does it help with fleet management? Something happens on the fleet side. It looks at that event. For example, let's say Uber, right? A lot of data being pushed to the data being pushed to the Flink cluster, and let's say it sees something in the fleet. Let's say some robbing is happening, or some unusual things are happening in that fleet. What it will do is it will analyze this particular stream, detect an anomaly, and um, and do something based on that particular event, I guess. Okay. or let's say personalization, right? So one of the things about personalization is, let's say a particular user is um, browsing on Amazon, looked at one product, looked at product two, looked at product three, then we know that looking at these three products, what are the products that we need to show next to that particular user based on these past choices, or however past choices that you want to look at. Okay. And anomaly and fraud detection that we already talked about. So, so what it does is, so certain event occurs. For example, fleet change. For example, it looks at certain transactions and sees that, you know what, there is this anomaly happening for this particular user's account. Then it triggers fraud detection and something like that based on those events. It could be anything, personalization as well, anomaly detection, fleet management. Okay, it's easy to say. Okay, that's fine. Okay, so how far can Flink scale? Flink is used at massive companies like, that's fine. And lift over use case double 11 single digit days 2028 Alibaba throughput 4 billion event per second. That's huge. Huge. State size 100 terabytes. Wow. Sub-second. Okay, infrastructure more than 15,000 nodes, 1.5 million cores. Nice. Execution can proceed in stages. Entire pipeline must be running continuously. Of course, for streaming processing, that's fine. For batches, for example, we are looking at, let's say, 10 terabytes, right? So, what? So let's say there are transformation which are happening. For example, we selected a particular table, we group by a particular column, right? So what it can do is, it can do that part in one transformation. Other part, other like after that, we calculate the count as we showed in the previous example. We can calculate the count in another stage. Okay, or maybe we divide this into multiple data. For example, 2 terabytes, something like that. I don't think that's what the stages mean. So stages is group by and then counts stuff. So that's one thing. Okay. But in streaming, it has to happen continuously for each message. This because we in the streaming, the main point of streaming is iterator. We need to provide an iterator which does that um, processing of each event continuously. But in batch, it's not required. You can do the processing completely, like at once, right? Input can be pre-sorted. Can be pre-sorted. Example, by timestamp or group time must accept regulator. Right, that's fine. We can do some pre-processing in the batch processing, and instead of stream processing, it's just straightforward. Whatever message we get, we need to process that. It can be reported at the end, must be reported continuously when ready. Correctness in the face of failure can be ensured by simply restarting a batch. Minus in the face of failure can be ensured by simple strategy. We need, so let's say we failed to complete some task, some stage. And what we need to do is we need to again process that stage from that particular input that we did. Just restart the particular stage. A batch, complete batch. Might be like that. Again, robust failure handling is hard. Why the handling of that message is hard? Because if let's say we are processing a particular message and we fail in the middle, we might have made some changes somewhere, or let's say we sent a mail based on that message. We cannot undo that. That's a different thing, I guess. Or maybe it's the same thing because it's streaming, right? So it's streaming, we process this message, we sent a mail. Or I think could be we made some changes, we changed our state based on that particular message and then we failed. So that particular state becomes inconsistent or yeah, inconsistent because that particular processing has failed and then when we restart that processing we will be redoing that particular processing again and as the state is not correct because we half process the last message, then it will cause a problem, I guess. That's what it says. Okay, so counting events per second. Okay, so event data is there, timestamp is there, second. Okay, the input is a batch of timestamped event covering some timestamp. What we can do is we can as we saw previously, we can just ask it to provide for ask all the event between that particular window between that window and in that processing of that the time window we can just count the number of events and just store those events. And in the data structure index, the timestamp that spans the entire batch. Okay, this is about after processing the entire batch. So this is for batch processing. What about stream processing? For stream processing, the timestamp could be jumbled up. If it is an unbounded, somewhat out of order stream, bounded, somewhat out of order stream of timestamp events. Okay, so counter must be accumulated in a bounded data structure that can somehow be pruned once the result for an interval is complete and has been reported. Okay, so counters must be accumulated in a bounded data structure. So for example, we are calculating the counts for the last 10 minutes right now as a buffer. In bounded data structure. Data structure, so this is the data structure. This is bounded and can somehow be pruned once the result somehow be pruned. The result for an interval is complete. So this interval, let's say this particular interval is complete, right? We can just move this out and has been reported. So this we report it and then remove it from here. Result are reported once they are considered complete. Okay. Streaming this becomes more difficult because we need to find a way to prune the data structure where we accumulate the counter once the time slot in the structure is far enough in the path. We shouldn't need it anymore, but this requires explicit support for managing time. Okay. Watermarks are Flink's solution to this, and we will look at this in details later. Okay, that's fine. Always on, always connected infrastructure. That's fine, highly available. Performance provides enough scalable performance to keep up with low latency and high throughput demand. That's fine. Fault tolerant. state that survives failures and restarts. That's one of the interesting thing, right? So it has a storage which is fault tolerant with high availability, right? And high performance, low latency, and high throughput. That means it must be writing that state change. Let's say if it is writing that state change pretty frequently, and if it is writing that state change pretty frequently, then how it's interesting stuff. Like how would they how would they how would they do that? Like how would they make that state consistent? Because it might be happening that that particular state change is replicated across multiple nodes, and those multiple nodes are at different VMs, right? Or it could be on the same VM, but if that VM goes down, then all those nodes go down. So I guess it will be at different VMs. But I guess what can happen is something like consensus algorithms, right? So what we can do is we can implement Raft, which has this write-ahead logs, which is replicated across all the followers, and they execute those logs in that same order as the master node says. So, but it needs to push that log. First of all, send that log to all the followers, and so it sends that log to all the followers, and when it gets, when it gets the confirmation from all of them or majority of them. How does it work? I forgot. Yeah, I think it's all of it's no, it's not all of them. It's actually majority of them because all of them is not possible. All of them is not possible because might happen that at a particular time a particular node or follower is down and it cannot reply at that time. That should not block the particular update. So okay, so it looks at the majority of whenever it majority returns yes, it logs it locally and do the transaction locally, do the state change locally as well. And after that it sends the success of that change, but that's something like that, right? So we can implement some consensus algorithm to make the change, but I don't know whether it's fast enough or not. What it might do is it might process lot of state change in parallel, or for example, time window, right? So let's say there is a 10-second time window and we're processing all the messages in 10 seconds and updating that state once for the 10 seconds, then it becomes a simple solution, I guess. Okay, so we're able to know when all the data for a given time frame has been this is it's a state. Flink does. So let's look at the right side of it. The Flink is designed to support daily continuous update, but nowadays to get daily recovery starts and away. That's fine. As we have already seen, Flink is highly scalable. Flink does its own state management and provides for dozens of periodic checkpointing. Other presentation will cover various aspects of the in more depth. I mean, it's fault relevant, but I mean, is it really? Because through periodic checkpointing. So, for example, it maintained certain state and during checkpoint for let's say last 5 seconds and the failure happens, that particular state is gone, right? If that particular state is gone, that's not reliable, is it? Other presentation recover is, but do we need it? Because it's streaming data, right? So, do we really need it? Give me a second. Because it's streaming data, right? So, So, okay, so able to know, okay, checkpointing, I don't know how effective that is because checkpointing is like a snapshot, and between the checkpointing time, it might kind of failure happens between the checkpointing that particular buffer. So it actually is okay. So it might be possible that there is a configurable way to change how frequent the checkpointing happens. And there is a trade-off there that if the checkpointing happens quite frequently, then you will see the processing happening very slow. And if the checkpointing is further apart, then then the messages will be processed faster as compared. Okay. Okay, so this is challenging because I don't know when all the data for a given timeline has been processed. Okay, this is challenging because in general, data arrive out of order. Flink solution relies on watermarks, which are discussed much in detail. Okay, so what? So whenever we say that it needs to process 10 seconds, right? But the data might come in random order, and we want to know that this particular range is done. So when do we know that? Because it might happen that a message in a particular range comes after 2 hours when the particular range was started processing. So if that happens, how does it do that? Notification is just sent. Yeah, okay, that's fine. Okay, so table able to know when this happens. Flink is an open source stream processor with fault tolerance. Um, exactly one stateful operations. So particular change happen that can be like, done with logs, right? Consensus algorithm, something like Raft. It's easier to do. Like now it's easier to do, I guess. But fault tolerance, checkpointing, right? So it's called snapshotting, and snapshotting. But that's for. So what did they say? Check following up reaction. Balance for log value. I don't know. Um, let's continue. I think we'll find our answer later on. Event time processing of real-time and historic data, that's fine. Highly scalable and performant runtime. Highly scalable and performant runtime. How does it do that? Layered APIs, expressive, easy to use. Rich connectors ecosystem. There are a lot of connectors which are available. Kafka connector mentioned, right? There are a lot of connectors. For example, CocosDB has its own connector. PostgreSQL has its own connector. So there is a lot of Kafka connectors which are there where we take the CDC data from these data sources and put them into the stream in certain form. So there is a yeah, there's a big ecosystem for rich connectors which are currently built for most of the databases, most of the popular databases at least. Um, the ability to efficiently run patch workloads. Okay. Efficiently run batch workloads. Okay. Okay. So this is basic. So let's look at basic transformation and how that is processed. Implementing basic transformation with data stream APIs. Okay, so filter map, flat map. So these are the three things that we are looking at. These are the stream, data stream which is coming. This is your code, one at a time event processing is done. Then this is the output. Long running computation and knowledge stream. Okay, so what happens? Let's look at this. So this is the stream execution environment. We from this environment, give me a second. Okay, so let's look at this from element 1, 2, 3, 4. We got these integers, and out of these integers, data stream of integers, we transform. This is the transformation that we are doing. These are integers, filter function. Okay, so this is the filter function that we're creating, which is taking integers, of course. Only returning integers, I guess. I think it's returning integers. No, it's Boolean, right? So it's taking integer value. It's checking whether it's even or odd. So if it is odd, okay, so it is okay. So this is integer. It returns integer, but it checks whether this is a filter function which filters all those integers, returns odds. Transformation filter which is happening, it prints those and it executes this particular environment, I guess, which returns 1 and 3. Okay, so this is a filter function. How does the transformation internally happens on this? So this is a complete example of the size of living chunks and authorize every Flink obligation using the data stream APIs. Needs a stream execution environment. This is a builder that assembles a job graph. Huh. Application the job graph. Print attaches a print string to the job graph and an ID. This will show result directly. In a cluster, each task manager will write results to a file in its log directory. Aggregate submits the job graph to a cluster for execution without okay, nothing happens. So something like this, right? So this is a like a builder class, which and this is the different DAG. This is a different operation which is creating the job graph, which is a direct acyclic graph of different tasks, and including this print also. And this particular DAG is actually submitted to the cluster when this execute happens. So this particular DAG is sent to different cluster nodes. Those nodes have certain data, either it's streaming data or it's data coming from some database, and it processes each those um, input and prints the output in a streaming fashion. Got it. So map function and flat map function. So this is from this events. This is like integer filters. It filter. So why cannot we do this? So we could have done this first, right? Why do we need to create this filter function like this? I don't know, maybe it's a simpler way. It is a simpler way. And what this map function does is it converts that it's a transformation which is happening, right? So it maps these each n to 2n, it converts that output. So double odds, it multiplies it by 2, so it will be like 2 and 6. So double prints and execute, yeah, okay. Flat map function, let's say this is map, this is flat map. Yeah, let's look at filter, flat map, the flat map filter function, I have integer. Huh. I think it's similar to what Java has, the flat map function, right? So this is a value, and this is the output. So if this particular satisfies the inputs into the output, and okay, and this is returned here. Huh. Memory has one-to-one transformation. Here we have changed the map to the filter and then the one-to-many transformation. Huh. So we are given an integer, right? And it uses a collector to emit 0, 1 or many result for each incoming event record. Useful anytime your function might have to cope with unpassable input or other error condition or whatever a single input record might produce multiple output. For example, if it needs to unpack an array or a list, for the example produces the same results. Okay, so if you want to have something like convert this integer to integer one-on-one mapping, you need to use map. If you need to use create one-to-many mapping of between the input and output, then you need to use flat map, which converts, for example, input is an array of 1, 2, 3, 4, right? And it converts that 1, 2, 3, 4 into an output, right? Many output. So it converts that into 1 and 3 multiplied to 2, right? So 2 and 6. These are the multiple outputs that is created and double odds print set. Why? So integers dot filter first it does, which streams this 1, 2, 3, 4 one by one in the map. And integers, it does it directly giving some stream out. Right? So it produces output, which is you might have the call. Okay, got it. Okay. So, for example, what we can do here is like we are just taking this output dot collect, right, and adding this value. We can also do something like out dot collect pass or odd. So those particular two values will come into the output as well. From one, we have created two outputs. So that's one thing. Okay. Okay. So rich functions. These functions interfaces have just one method. They can be implemented as Java lambdas. Okay, that's fine. Each has a rich variant that implements a rich function interface. Rich filter function, rich map function, rich flat map functions. A rich function has this additional method open, close, get, and time context. Huh. Okay. So one is called Once during the instantiating load involved during cluster shutdown. Cluster shutdown. So during the initialization of that function, we call open, and during the shutdown of the cluster, we call close. Get runtime discussed a bit later in this track. There's also rich co-map function and a rich co-flat map function for operating on connected streams. These functions have two input streams. Have map1 and map2, or flat map1 or flat map2 method. Methods for processing arriving events from each of these inputs. Huh. Operating on connected stream. What does connected stream means? So let's say there are two streams which needs to be processed at the same time by the same function. Then it needs to like input stream. So these are the map1 and input stream that are processing arriving inputs from each of the input. Okay, the process function or key process function, etc. is called a rich function. Okay. So there is a category of functions other than map, flat map, filter, which are which variant of these, which are called rich map, rich filter, rich flat map. And these rich functions have open, close, and get runtime content. Get runtime constructs will be discussed later, but open and close is there. Open is called when we initialize the function, and close is called when we shut down the function. Okay. Okay, so there are other functions called co-map or co-flat map, which actually uses multiple streams, multiple connected streams to be processed by the same functions. And yeah, so let's look at some examples. Here's an example of a rich flat map function that loads reference data in its open method. Huh. So reference data set in its open method, which it holds in memory and uses for enrichment. So for example, so you have created this enrichment with preloading function, with a rich function, flat map function which we have created, which takes event and it returns enriched events. And when we call the open on it with the configuration parameters, it opens that parameter, load the reference data into the reference data. In the reference data is like long and sensor reference data. And then there is this flat map function which is overridden, and what it does is it gets for each reference data it okay, no. So there is an event. Hold on a second. So what it does is the reference directions to the sensor measurement that gets sensor ID. For this particular sensor ID, we get the source reference data, we put it in the collectors as an enriched event. So event is given, sensor reference data is given, we enrich that particular event. So for example, let's say the event has come that this particular user is at this location. So what we do is, or let's take another example. Um, let's say we want to geotag all of the events, or we want to enrich a particular geotag data to include all the information from that message, right? Whether from which location it is coming from, um, or any kind of enrichment that we can do on that data based on that location. Or we can try to, what we can do is, um, for each message, I'm looking for an example. So for a location, we can enrich the data by, for example, restaurant, right? We can enrich that data by finding all the restaurant which is near to that particular location, and we can store it. So whenever that particular user opens the app again at that particular location, we can provide that all the restaurants which are near that restaurant or something like that. We can enrich the data. Previously, enrich the data in open method. So in open method, it loads the data. So this is the data which we can load in memory. Already existing data. It's not coming from the messages in runtime. It's already there. We just need to load it and locally in the map. In this case, in the map in memory. And the runtime function has many other functions such as get index of the subtask. Huh. So, so the context is there, which tells you what's the index of the subtask in that particular graph, in that particular DAG graph. Okay, the number of parallel subtasks which are going on. Get execution config. Okay, provides access to key partition state via get state. So what we can do is access to key. The runtime context is the gateway to access all sorts of interesting information about the environment your job is running. Of particular interest is that the context, runtime context gives us an access to the state backend, which is where the flag managed state is recorded. Stored is stored. So it can give you the state. For example, so we can store the state. We can, like, there is a state which is mentioned, and we can access this particular state using this context, I guess. So access to the sharing, the runtime context gives us. Okay, so we can access the state here. So what do you call this then? This, is it not a state? I guess this is not a state, which it can be maintained across different functions. So this is definitely not that state. Maybe a state is, yeah, mentioning like how many transactions that particular user has done in last 5 seconds, something like that, which is like a global state which is mentioned. This is a stat which you can get from this, I guess, or manipulate from this. So what output does this produce? That's map print. Okay, 246. Okay. Why is it not displaying? Because it's inside the. Huh. Okay. So this is a new stream that it creates a new stream, but we are storing it here only. So it will return 1 to 3. Come on, man. There is no output here. Okay. So use from material or from collection to create a register to expand when we use print to print a data stream. Lazy execution can make debugging tricky, but you can use breakpoint in your ID. Okay. Let's go back to Flip runtime. So this is what Flink looks like internally. So there is a logging service, there is a telemetry service, let's say metrics, right? There is a task manager which is given I think a job graph, something like that, or individual task inside each, like inside the graph. So so there is a global storage, checkpoint storage. There is this task manager which executes each task, and there is this job manager which execute each job, which consists of task, I guess. And there is usually a high availability service. So HA service will have storage for cluster metadata. Give me a second. Let's come back. Okay, let's start. Okay, so HA service stores metadata about the cluster. Storage for cluster metadata used by the job manager. Storage for cluster metadata used by job. Job manager needs to know. Job manager needs to know where. So it needs to know where it needs to send different tasks in a job, right? So it needs to know the IDs, identifier of each nodes which are currently running. For example, each task manager IP address or machine ID to know, it needs to know those information, right? And it is to know in real time. For example, a job manager is trying to figure out that this is a particular DAG. We need to send these tasks to this task manager, these tasks to this task manager. It needs to know where those task manager exist, or how many task managers are free, or um, what's the health status of different task managers, context about what are the IP of task managers and all of those stuff, right? So it uses HA service to store those information. Of course, Zookeeper, provided by Zookeeper or Kubernetes config maps. Okay, I think the Kubernetes config maps also implement something similar to Zookeeper. Zookeeper has high, I don't know whether Zookeeper has high availability, right? So it has high availability, but it doesn't have linearizability. For each client, it will have linearized storage because it allocates internally. For each client, it allocates a particular node, which could either be master node or slave node. So the linearizability comes for each client. So each client will see things happening in a particular order, and two different. It's not necessary that two different clients are seeing things happening at the same time, but it will happen to them in the same order. So that's another thing that Zookeeper does, and there is high availability. I don't know whether I don't think Zookeeper has high availability if you are writing something. So if you want to write, it has to go to master node. First, it goes to the each node which is assigned to each client, and then it goes to the master node to actually execute. Queued on the slave nodes and executed on the master node. But if the master node is down, then those writes cannot happen. So the high availability decreases, right? So it's the standard master slave configuration, which not exactly really high availability in case of master failure. The election we need to do election as well. Sometimes those are hard coded or given in a priority or depends on the state of each slave, or those are the stuff that is implemented. But there is like another way of implementing it is using consensus algorithms, something like Raft or Paxos, which elects the leader and by consensus across different nodes. And then I don't have the statistic which is better, but I think overall um, highly available and highly available elections and with consensus is done with like Zookeeper also has something like, right, so for example in case of Raft, if the master node goes down, some other nodes inside the cluster which is still running and has up to date data is made the leader. Okay, but in case of master and slave, okay, in Raft it is made the leader after doing the election across the nodes which are alive right now. And in the consensus happens between those nodes that you know what, this is a particular node which has my vote, and this is what this which has my vote for becoming the next leader. But that doesn't happen in master slave, in which any node can say that I am the leader and start executing as leader. So in those kind of cases, there is a possibility of split brain happening. But in case of Raft, it doesn't happen. So I don't know why they still use Zookeeper. Maybe Kubernetes config map has the particular Raft implementation. Zookeeper doesn't have for sure. It uses something called it provides a total order on the storage. use like broadcast, use a broadcast protocol or something like that. I forgot. Broadcast order protocol to implement. Anyways, provided a lot of information which is not necessary. But so job manager is like a cluster manager. It sees a particular job, it sends that particular job to, it divides that particular job to task and sends those tasks to each task manager and execute the task, which executes those tasks. So task managers are workup. So of course, this is okay. Task manager worker process is running the user code. So each node in the tag is given to a particular task manager node, and that particular task manager has the user code and runs all the database. It runs that particular function on all the data input data. Checkpoint storage, distributed file system S3, SDFS. There are like Amazon, Apache, Iceberg as well, which has this storage. I don't know whether this storage is for Apache. Anyways, so we'll look at Apache Iceberg as well later on to see how it works and how it provides storage options uh, internally as well. So look at that and how it integrates with the Flink. Metrics and logging, CI/CD, optional component. You can configure one or more metrics reporters for connecting to systems like for connecting to systems like Prometheus, Gemini, Graphite, etc. So let's see Prometheus what is stat sd. Okay, so it aggregates stats and hmm. Okay, numeric times is data in the grammar data. Okay, so they're saying that we can plug in these different metrics reporters to get different statistics uh, from our system, from what we are executing, right? Let's say we want to see how much time a particular task is taking on average. So we can like optimize that particular function of that particular task. Logging and metrics. External component that connects to almost everything, hence the funny shape. Yeah, that's fine. Not showing all of the data flow, that is the source sync and data exchange between task managers. Yeah, so that's one of the things, right? So let's say in the DAG, we need to send one output of one task to another task in the DAG. So how do we transfer that data? Do we transfer it through the checkpoint storage? Yeah, right, because that's the state that we are maintaining across. But there there is like for example, let's say there is a message which is converted into another form, which is converted into another form, which is converted into another form, and that message is passed across, let's say those three different versions of messages passed across three different versions of some tasks. So it needs to output that task from one task to another task provided as input in that task, and So it cannot store that in a state because state doesn't, that's not the state. This is the transit data. So your different task manager needs to communicate. So these task manager will communicate somehow. And this task manager needs to tell job manager when a particular task is done or not or failed. So that's the communication there. And this job manager will provide will read from the checkpoint, provide this checkpoint this state to the task manager because it needs to manipulate the state and this task manager will store that state here. So that's one thing, but there is a contention which will happen here. But let's forget about that. Let's for now. Um, okay, so let's look at the next stuff. Okay, that's is good. So distributed runtime. There is a client, Flink client program, program code, data flow program, graph build. We have built program, data flow graph, graph builder, job graph. The client has a job graph. That job graph is submitted to job manager, which has these scheduler check. This standard job manager it looks like it. So, um, so there's a scheduler. So, for example, this is a DAG, right? So there is a topological sort in the order in which we need to execute these tasks. So, for example, the topological sort. So we can execute multiple tasks at the same time to parallelize the task. If those tasks doesn't depend on don't depend on the output of each other, right? So we can execute those tasks. So this is what the scheduler does. So it takes the like there's a DAG. It creates a topological order. At each time it can execute this particular task. It schedules out tasks across the different task manager which is present. And there is another component called checkpoint coordinator, which checkpoints the state of each job. So how frequently it is depends on the configuration, I guess. Uh, so there is a dispatcher which dispatches a particular task to a task manager. There is a resource manager. Okay, so job manager has several components. The dispatcher, the REST endpoint for the cluster, receives job. Okay, so receives jobs from the client, starts various per job components for each job. Okay, the scheduler slices a job graph into parallel tasks. That's what I mentioned, right? Slices the job graph into parallel tasks and schedules them for execution using resources obtained from source manager. So resource managers tells these are the task manager which are present, these are the health of these task manager, something like that, and tells you a particular number of. So you can send. So if you need to execute these many tasks, you can use these task manager and execute those or schedule those. You can execute the like, looks at like for example, we have to execute three different tasks, and we tell resource manager, you know what, give me three different task managers. And what resource manager does is looks at all the task manager which are present. Let's say there are 10 task manager which are present. Then what it can do is it can actually provide the best three possible task managers and send assign those tasks to those task managers. Trigger checkpoint coordinator triggers checkpoint, keeps track of the liveness of the worker. Okay, why does it do that then? Initiate restarts as necessary. For example, a particular task gets stuck or something like that, right? So there is a timeout which happens, or it is not returning the output of it. Then it cancels that and restarts that particular task. And This sends this task job to task manager. The task manager has this task slot which contains the task. Data stream which happens between these task managers. You guys calculate running task slot. This is the unit is the unit of scheduling. Okay. The task slot provides resources for running one parallel slice of your operation. Well, it provides resources for running one parallel slice of your application, one or more cores and some memory. The task slot is like containers in which those operations are running, and those containers are and so those containers are resource limited, cores, CPUs, sorry, core CPUs, RAM, and all of that file systems. You can mention that in the config, I guess. And the config is present in the HA service, which is saw earlier. Mini cluster. So, what is mini cluster deployment? Okay, so mini deployment model, mini cluster, single JVM with client, job manager, task manager, convenient for running tests and debugging. Session cluster, long-lived cluster, multiple jobs, no isolation between jobs, task manager are shared. Yeah, so for example, um, for two different jobs, which contains two different tasks, can be executed by a single task manager. Though the isolation doesn't happen at the task level or the job level. No, it happens at the task level because those are executed in different containers, but it doesn't happen at job level. Yeah, so well suited for running many short-lived jobs. Analytical queries. Okay, job cluster. Long-lived customer jobs. Well, a single job cluster lives and dies with that. Okay, so this is like a live job, a live cluster which is created for each job. Unlike Lambda function which AWS has. Well suited for jobs that runs continuously. Hmm. This is a long-lived cluster and is better for short-lived jobs because for short-lived jobs it takes time to bring up the cluster and bring down the cluster, right? So that will not work with the job cluster. For job cluster, it's better that the task is long running because the time it takes for the cluster to start up and close down is very less as compared to the main job, which doesn't waste our resources. So yeah. Mm, okay. So what is another thing? Application cluster, new and link 1.11 only executes job from one Flink application. From one Flink application, only job from one Flink application. Sorry. Only executes job from one Flink application. Okay. Main runs on the cluster, not on the client. Okay, so it's like a jar it creates locally, and that jar is sent to the. So it's like an application, right? Everything is run on the particular cluster, that particular job. sorry, whatever in that job is run on that cluster, which is called application cluster. And yeah, can deploy Flink app on yarn like any other yarn application. Okay, irrelevant. Anyways, so data stream API and execution. So it has this source, it has this event, it has the stats. It is the thing. We have already seen this, right? Yeah. So let's say this is a graph. Okay, this is the graph. Okay, so main takeaway, you see that in the polygon, okay, fine. Against flow between nodes in a graph, we can, okay, source, okay, filter and transform, state read and write, and set. Event stream flow between nodes in a graph. We call these graph nodes operators, and set of nodes corresponds the set of nodes corresponding to a running application is a job graph. Okay, so for example, there is a source, file transform, it transformed, like it filtered some, transformed some, and provided the output to. So these job graphs are run in parallel. So these job graphs run in parallel. Here we are looking at the physical graph or execution graph for a job. Flink provides very granular control over the parallelism, which can be set for the entire job as well as for each operator. Here we have chosen to have parallelism of 2 throughout most of the job, but the sync is single-threaded, not because it's a good idea, but just to make the example more interesting. The second and the third layer of this execution graph, the filter and the read-write operators are fully connected. So this particular filter node is connected with both of them, this particular node is connected with both of them. Here we are performing a fully connected data exchange. Here fully connected data exchange between the workers, sometimes called network shuffle. Here we are performing a fully connected data exchange between the workers. So I give an example, this is the work. Okay, so these nodes are at different, these nodes in this graph are at different task managers, and there is a data transfer which is happening between these task managers for network shuffle. The data is being partitioned around some specific data is being partitioned around some specific key so that each of the stateful nodes will process all of the event for some of the key. Okay, for example, you might be processing an event stream from a mobile app, and we might partition a key we might partition or key the stream by user ID so that we can gather statistics about each user. So, for example, a particular user ID, it will be stored there. It will be stored there for each. I guess, and the partition happens. For example, we process a transfer. We want to store a particular thing at so a particular. We are going to change the state for a particular user ID. For example, we did some parsing. We extracted some details about the users. We want to store that particular state of that particular user, so it is connected to both of them. So if this particular, so it will send this data either to this or this, or if similarly for this particular node. I think I understand it. Okay, so let's take an example. Event stream maintain the relative ordering. So if they take the same path through execution, and notice what happens to event when it takes a different path through the graph than one and two. Let's see. So from when it takes different paths to the graph than element two. Okay, so it comes to this, which is filter. It sends this to that because okay, and okay, so the stream ordering changed. We produced output data exchange strategies. So okay, let's dive into some terminology used in Flink. These are different patterns of data exchange that can exist between operators. These are different patterns of graph. Including operators in a job graph. Forward, the current partitioning remains unchanged and each record stays in the same parallel instance. Okay. Okay. Key waste. Okay, so if let's say it's just a forwarding data exchange, right? So if it is just a forwarding data exchange, it will go in the same order. But if it is not, then it will be partition based on key. The record are partitioned by some logic that computes a key for each record. Records with the same key are guaranteed to take the same path. That's fine. Broadcast. Everyone gets everything. Okay. Round robin. So it's like the records first is sent there, second there, third there. Goes are sent to each down the order in turn one after another. This is, for example, when doing debugging to effect change in parallelism. Change parallelism. So that's nice. So there is forward, key based, broadcast, round robin. Okay, so we have job components, operator component, operator chaining. So chaining. Let's look at the diagram first. So source map, operator chain, operator, operator, task, task, task goes to thread, each single thread. Task goes to thread. So source and map is merged. Okay. Chaining the records are passed from one user-defined function to another without any other lower layers of Flink getting involved. Deserialized serialized network stack. So records are passed from one user-defined function to another user-defined function without any lower layer of stack, lower level of Flink getting involved. How does it pass that though? Hmm. Increases throughput, no serialization on network. Okay, only possible during forward data exchange. Because everything which comes, which is processed, let's say output happens, then that output is directly transferred. It's not manipulated in any way whether it needs to be passed there or not. It doesn't look at actually the content of it. It just pass it forward. And if you want to do anything else, um, as a key based, we need to look at the content, and for which we need to parse it at the network layer, at the application level. So forward layer seems fine. The chaining can be disabled. This is normally only done for debugging purpose. For example, you might want to force the network to be used to make the communication between two operators more observable. The job graph is sometimes called logical graph, and the execution graph is sometimes called physical graph. So one parallel instance of an is called operator is called a task. Each task is single threaded. Okay. Sometimes tasks are referred to as subtasks to emphasize that there may be many instances running in parallel. That's fine. See the closing for these other document reference. That's fine. So these are the tasks chained, chained, and this is passed to this. It is happening on the main thread actually, so it doesn't go over the network. It is on that same particular VM, same particular thread, which operates across these two different subtasks. Execution graph is scheduled into task plots. So each layer, right? So this is passed to this two is passed to this two, and the sync is there for this. So it needs to pass the output to here at the end. So here we see this job deployed with the parallelism of 2 except for the sync which is running with parallel 1. This cluster is running in a typical configuration with one slots per task manager. Each task slot has been assigned um, 2 or 3 tasks to execute. Each task manager is running in its own VM. The VM each task uses one Java thread. Turn this off. And the 2 or 3 tasks in each slots are sharing the resources provided by that slot. Okay, so these are not happening in parallel because we need to provide an output for it, right? So each task uses, so chaining is done there. It needs to execute the task, and after that task, the output needs to be sent. State change, right? Okay, that's fine. Each, each task is running. Each task uses one Java thread. Yes, uses one Java thread, and the 2 or 3 tasks in each slot are sharing. So by the slot, we got slot sharing. So each of these threads, okay, so the output for this needs to be sent to either this or this. So if it is this, which is forward chaining, this is forward chaining, right? So output of this will come and needs to be signed, let's say, based on keys. So it can go here as an input to this and input to this. So, okay, as manager is running a JVM, okay, this cluster is running a typical configuration. Region one slot for terminal, each task slot is inside to create task, and each task uses one Java thread. So in the same JVM, each of these tasks will have one thread and task in each slot is sharing resources provided that slot. So each slot has certain resources. So this is a particular task manager which has one JVM. JVM has certain resources which is provided to this task slot. Each task in the task slot is executed in separate threads, which uses the resources provided by task slot, shares those resources. This is called slot sharing. The task slots are simply an abstraction for scheduling. They don't correspond to anything physical. Whatever resources a task manager happens to have are used by the slots running in the task manager. Okay, so this is more open. I don't know what this is how is it managed. So for example, how is this managed? For example, let's say this thread uses all of the resources and deprive these threads to use those resources. Then it can actually kind of block the execution of these two, right? Even though it is sending the output to this, it will not be able to execute it. So the streaming will not work. So we need to manage these threads as well. How much resource you want to provide to the threads. Okay, so I think we are done with the intro part. Uh, I think this is a good stuff. I thought it was a little bit more complicated than this. Maybe the complication will come later on. But yeah. Um, so in the next stream, we will look at the state, time, SQL, and wrap up this particular developer training. And then we can look at the code. We'll do some coding based on IntelliJ, looking at different issues that is currently Apache Flink has. Okay, bye.